The easy one. Let's ask, what does the, and I'm going to highlight here so you can see, what does the plus d do to the logarithmic graph? Can I please have, let's go with Olympia. What do you think the plus d would do to the graph? It doesn't have an asymptote. It does for an exponential, but not an asymptote. What does it normally do? Yes, Ed?
Transforms upwards.
Good. Translates up or down. Anything that you're adding to the equation, anything you're adding to the equation separate from the equation from the function will move up or down. So an example would be, if you remember, y equals, let's say, x squared. If I did plus 1, moves up by 1. If I gave you y equals root of x and I said plus 1, it moves up by 1. If I gave you an exponential e to the x and I said plus 1, it moves up by 1. So therefore, if I gave you y equals log base e of x and I say add 1, it's going to move up 1. Okay, so the plus d here represents up or down. When you add, it goes up. When you subtract, it goes down. Now, that was the easiest one to pick up. The next part that I want you to think about is, what does a do again then? So think about all the functions that you learned. X squared, your radix, your square root, your exponential. What do you think if I put something multiplied to the equation? So a, what does a do? If I said 2 times x squared, or 2 times root of x, or 2 times e to the x, what does 2 do?
It's the factor of dilation.
Yes, it is a dilation to stretch. Now, is this a stretch from the x-axis, or is it from the y-axis? Which one is it? What was that, Finn? From the x-axis. It's affecting the y's, because remember, if this was y equals to x squared, that's what y is, right? If I put a 2 times that, I'm actually just saying 2 times the y, because this is what y equals to. So if I did 2 times x squared, it's like saying 2 times y. Therefore, if you're affecting your y values, it's your vertical stretch. Okay, so this is a dilation factor. So you're dilating factor A from the x-axis, meaning it's a vertical stretch. If that didn't make sense to you, it's a vertical stretch. Okay, so in most cases, like a quadratic, will make it look thinner. Okay, but what else can A be? So not only does A do, so when you times it by 2, then it makes it thin vertically. What else does it do as well? If you're timesing, what else can you times that is also part of A? So if you have dilation, it's not a translation, it has to also be, starting with R.
Oh, reflection.
Reflection. See, when you're timesing, you can times by positive numbers, or you can times by a negative number. So if A is a negative number, you now have a reflection. So here, I'm just going to write down here, if A is negative, it is a reflection. Now the question is, reflection in what? Is it a mirror in the x-axis, or is it a mirror in the y-axis? Which one is this one? The only way to figure that out is, which one is it affecting? See, when I put a negative on it, am I affecting the y or am I affecting the x? Because if you can figure out whether it's the x or y, then you can tell whether it's reflecting from positive y to negative y, or from positive x to negative x. Then you know which reflection it is. So if I put a negative there, negative times a log, is that a reflection in the x-axis, or is it a reflection in the y-axis? Which one is it? Which one is it? Anyone have a clue? What? No clue. It is a reflection in the x-axis, because you're dealing with the y's. Okay, so remember, if A was a dilation, if it's a vertical stretch, means that you're multiplying the y values. If you're multiplying the y values, that's why it's it's stretching. Yeah, so stretching all the y values up. Then it's the same thing when you put a negative, then it's negating all the y values. So if you take all the y values and you put a negative in it, it has to reflect on the x-axis. Okay, so if you think about a picture, think about the x-axis. See, if I put a coordinate here, I said 1, 1, I said reflection on the y values. So if I put a negative on the 1, it now becomes 1, negative 1, which is why we call it reflection in the x-axis. Okay, so yes, it does deal with the y, but it's not reflection in the y-axis, it's reflection in the x-axis. Okay, so that's your A. Now, the easy part, in my opinion, is the easy part. We've done all the y's, now let's look at the x's. This is the stuff that you're dealing with the x's. So here, b multiplies to x, and you got plus c to the x as well. It's what you're doing to the x values. Just like with your square root function, that's your x. X squared, that's your x. E to the x, that's your x. Every time you affect your x's, it's your horizontal axes, boys. If you affect your horizontal axes, there's a few things you could do. You can either move it left, right, or you can stretch it horizontally. Okay, if you can stretch it vertically and you can move it up and down, then obviously you can do it horizontally as well. If you're affecting your x values, you can either move it left, right, and you can stretch horizontally. So the question is, how do you know if it moves up, down, left, right, and how do you know which one is responsible for a horizontal translation? Okay, so let's have a look. You got bx plus c. How do I know if it moves left or right? What do I have to do again? What's the trick I gave you?
Let x equal 0.
Yes, let the whole thing equal to 0. So you got bx plus c, let it equal to 0, solve for x. Now if you solve for x, whatever the answer is, if it's negative, it moves to the left. If it's positive, it moves to the right. Okay? So that's how I've been teaching you throughout quadratics. I kept saying to you, whatever you're dealing to the x, let it equal to 0. So this one, let it equal to 0, let it equal to 0, let it equal to 0, let it equal to 0. See where I'm highlighting? I'm just highlighting what you're doing to the x. Anything you're doing to the x, that's what's responsible for moving left and right. So let that equal to 0, let that equal to 0, let that equal to 0, let that equal to 0. If you want to relate it to chapter 7, see all I'm doing is I'm focusing on the old x. Whatever you're replacing it, that's the new x. That's the transformation. So when you replace the old x, that's why it works. That's why I'm focused on the x's. Okay, that tells you the transformation for the x's. Okay, so now you know how to solve whether it moves left or right. Finally, just the last step. What's a b do? If I put a b, so change it to 2x instead. What does the b do when you multiply a value to the x coordinates? What do you do? What is it doing? It is a dilation, and just be careful. Yeah, from the y, dilation from the y-axis. The only one thing you have to be careful of, when you're dilating from the x-axis, remember, it's not a factor of b, it is a factor of what? Finn. It's a factor of what? For b. We don't say a factor of b. I've been showing you that every time you're trying to solve for b, it's not a factor of b, it's a factor of? No idea. And this is one of the hardest parts. That's why I wanted you guys to pay attention here. When you're talking about a's, we normally say dilation of factor a. So if it was 2, you say dilation stretch double. But if you put a 2 in front of the x, and I showed you previously with the exponential graph, if you put a 2, it actually isn't stretching, doubling on the x-axis. It's actually halving. And if you remember why this happens, it's because when you're doing chapter 7, if you let this whole thing as x dash equal to x, and you rearrange it, if it's times, you rearrange it, you divide. That's why the x's have now been divided, and that's why it's different. Whereas for your y values, you find that you divide and then times. That's why it ends up being the same. Okay, so the one thing, just be careful, b is a dilation of factor 1 over b. Okay, so I want you to copy that down. Dilation of factor 1 over b from the y-axis. You're right, it is from the y-axis because you're dealing with all the x values. But instead of multiplying it by a factor of b, it's a factor of 1 over b. So what I'm trying to say as an example is if I gave you y equals log e of 2 times x, okay, versus y equals 2 times log e of x, they're both different. This one would be a vertical stretch, doubling the graph. So I'm stretching it vertically by doubling all the y values. Here, you're not doubling all the x values, you're in fact halving all the x values. And I'll show you in the graph, you can see it shrinks rather than expands. Okay, so that's why that is a half, not a factor of 2. And you'll find that you'll practice more of that next year as well. And that's one of the hardest ones for students to get. It's dilations that is tricky. Reflections you'll pick up. Anything to do with the x, it's a reflection of the y-axis. Anything to do with y, reflection of the x-axis. Translations most students will pick up. The easiest one is up, down. All my students in year 12 will know up, down. Not all of them will know left, right. Most of them will know reflections, but a lot of them won't know dilations. And it's just one of the harder ones to pick up. Okay, so I'm trying to teach you now just to focus. It's on the X or it's on the Y. Okay? Now, hopefully you've copied most of what you needed to know for the transformations. Now, we're going to play around in GeoGebra. You write your own notes here. Okay, I'm going to play around with all the numbers. You write your own notes on what you can pick up and what you remember when I change it to decimals, when I change it to negatives. How does the graph change? Okay, so let's have a look. This is your graph. That's your normal log. This is your equation over here. This is your equation. Okay, I'm just giving you an equation where it is y equals to log base 2 of x, essentially. That's what I'm writing there. Okay, I'm going to change all the a values. I'm going to change all the b values. I'm going to put in a plus d value, and I'm going to put in a plus c. And I want you to tell, or just write in your own notes, how do each of these letters change the equation? Because if you know how it changes, you can visualize the graph. If you can visualize the graph, you can analyze it. Hence, application should be easy. So after this session here, after the session today, you should have all the basic skills to do logarithms and exponentials. You have algebra, you have sketching. You have algebra for logs, you have sketching for logs. So by the time you get to the applications, there should not be anything I need to teach you after that. Application is just putting everything together. Okay, so it's really up to you to get your basics right. Your algebra has to be good, and then your graphing has to be good. Okay, there's two parts to that. So let's have a look at this. I'm going to change. First one, I said D was the easiest one, right? D is the amount that I add on to the equation. So this is log 2 of x. If I add anything separate to the function, it should move up and down. So let's see. If I change D to, let's say, 2, see I put a plus 2 there, the graph moved up by 2. Asymptote stays the same because I haven't moved it left or right. It's still asymptote at x equals 0. Can never have a negative value there. So I just move the graph up by 2. Okay, but there is no asymptote here. It just keeps going and going and going and keeps going up. Okay, so watch. As I increase 2, it will just keep moving the graph up. So watch. I'm going to move 2 to 3 to 4. You can see it's just shifting up, but nothing else changes. Okay, but watch out. When I put negative, it will just go down. So that's why it makes sense that the number here, D, I said it represents up or down. Okay, but you can't show that. When you're doing your graphing, you don't say down by 4.5. You just got to show it's down. Okay, but you can't point out a coordinate or anything. There's nothing that you got to label. You only need to label asymptote, axis intercepts. Okay, now asymptote is obvious. It's at x equals 0. Our x-axis intercept, you're going to use algebra from 13E to solve, which we'll do later. Yeah? Okay, so we now know this is up and down. Now I'm going to make D equal to 0 again, so we know that D is responsible for up and down. Now, how do we move left and right? I told you that if you change the B and C, it will determine whether it moves left or right. Now watch. When I make it equal to 1, C equals 1, what changed? My asymptote. When that's equal to 1, now I told you, how do you know if it moves left or right? Let that entire x bracket, anything to do with the x's, let it equal to 0. If you solve for x right now, you've got 1x plus 1 equals 0. If you solve for x, what would it equal to? What x equal to? Negative 1, which makes sense why my asymptote is negative 1, because I moved to left by 1. Okay, so if you solve the brackets, I'm just going to highlight it here so you can see. My technique that I've shown you since quadratics, since we started quadratics turning points, I said let the brackets equal to 0, solve for x, and you can see this will tell you that it moves left 1, which is true. The asymptote has moved left by 1. But watch. When I increase 1, you see, if I keep increasing, it just keeps, whoops, not that one, C. If I increase C, it just keeps moving to the right. I mean, to the left. So if I plus it, plus by 8.9, asymptote's at 9. If I now minus it, you see, if I minus it, on the other hand, it goes to the right. So it's just moving left and right. That's all it's doing. Left, right. And all I've changed is what you're doing to the x's. Anything that you change the x values will affect horizontal, vertical translations. Now, what I want you to see is, well, this is currently at -6. So if you solve for x, it moves to the right 6, right? Asymptote's here. So asymptote is right at the 6. But I want you to see what happens when I change. So the b being 1, so this is a dilation factor. Dilation is a horizontal stretch. You can either make it smaller or you can make it wider. Now I said to you that if you change that number to a 2, it's not doubling the x values. In fact, you're halving it. You watch how this changes the asymptote. So watch when I change it to a 3. I want you to see when I change this to a 3, look at what happens to the asymptote. See, 3 didn't triple my asymptote. It didn't go to 18. From 6, when I did 3, it's actually a 30. That's why I said it's a dilation factor of 1/3 B. Okay, so you can see if you did a third of 6, 6 is over here, a third of 6 is 2, which is why it shrunk. You're really compressing it. It's a horizontal compression. Okay, so B, it's the reverse. Whereas if you will look at A, see if I go back to A now, dilation for A, so I'm going to go make this back to 1. Watch A. So starting from the 6, watch what I do to the A. If I change this to a 3, or yeah, you see how it was a vertical stretch rather than a horizontal stretch or a compression. It's now stretching that way, but the asymptote stays the same because I haven't affected the x's. I'm affecting the y values. So that 3 there multiplied to this entire thing, that's not affecting my x's. It's affecting my y values. Because I'm affecting my y values, all of these coordinates are getting stretched vertically. As opposed to when I changed that to a 3, it was compressing all the x values by a third. That's why it shrunk and the asymptote moved over here. But the asymptote doesn't change here because I'm not doing anything to the x's. Okay. And it's the same thing if you wanted to know where the asymptote moved, even when this was a 3. So I'll just go back to 1. I change this back to a 1. Whoops. 1. And this back to a 3. See, my technique still works when I tell you, if you don't know how to read your dilations, you can still say, if you let this equal to 0, solve for x, x is equal to 2. It still tells you it moves to the right by 2. To the right by 2. So hence asymptotes at x equals 2. Okay? Yes, Finn? Yep, that's good. So let's say this is my C. Watch what happens when I change B. And it's meant to be a compression. The larger I change this number, it's just going to compress it even more. Okay, so watch. I'm going to keep the asymptote still at 6. So C is still 6, right? So I'm going to keep this. So if this was 1, x is still x minus 6. So asymptote still at 6. But watch when I change B. Sorry? Yeah, I can make C 0. So let's say I make C all the way back to 0. So asymptote's right at the center. Now watch when I change B, it should just be a horizontal compression or stretch. Okay? Now increase B, watch. It compresses the graph towards the y-axis. See how it's getting squished into the x-axis. The y-axis. Whereas if I make it a decimal, now watch this, when it's 1, so I'll go back to 1. When I make it a decimal, when it's a fraction, it should stretch out. You should stretch all the x values out. So watch how it gets a horizontal stretch when I get a decimal now. So 0.7, see how it's getting stretched out? If you look on the x-axis intercepts, it will be very obvious that I'm stretching it out. See, from half, if you did 1 divided by half, what's 1 divided by half? How many halves in 1? 2. So that's why I'm doing a horizontal stretch of factor 2. And that makes sense. See, that was at 1. 1, 0, if you times the x values by 2, it's now 2, 0. Okay? Because that is actually the dilation of factor 1 over b. So whatever b is, it's a horizontal dilation. So it's either stretching it out or it's compressing it. And it changes the 1, the x-intercept. Now watch, when I change, so this is the difference between, horizontal stretch and vertical stretch. Watch, look at the x-axis intercept. It changes because I'm changing the x values. But watch when I change A, which is a dilation of the y-axis, or changes the y values. Look at the x-intercept. Doesn't change at all. See, the x-intercept is still 1. Because you never change the x values, you're only changing the y values. So if you look at it, it's really clear that it's a reflection or stretch away from the x-axis. Okay, it's really getting stretched out or it's compressed towards the x-axis. So if you change this to, if I made it very small, so I made it smaller and smaller and smaller, you can see it's getting closer to the x-axis. If I stretch it out, it gets further away from the x-axis. And that's very different to this kind of dilation, when you do it to the x values, this one now compresses to the y-axis or away from the y-axis. See, that's the difference. Okay, so there is a difference between the A and the B's. Does that feel it makes a bit more sense? So now same thing with reflections. Reflections were negative. So if you times a negative to the x values, okay, so if I made that instead of a positive 1x, if I made that a negative x, see, I'm affecting the x values. It should flip on the y-axis because all the x values are now changing. So watch, when I change it to a negative now, it swaps. It's a reflection of the y-axis. So negative of x will switch it, reflection of the y-axis. Watch when I change y values though. So if a was a negative 1, so if you watch at a, so if I change a to be a negative, it's now reflection in your x-axis because all the y values are being affected, not the x. Okay, so the graph goes down. And if you want to do both reflections, then now it looks like this. That's both reflections. Okay, so both x and both y's. Cool? Now the only one thing I haven't described yet, what's the one thing I haven't described so far?
The base log.
Base log. That's the only one that I haven't talked about. And you can use what you understand from exponentials to predict this. See, when it was base 2, you go like this. Base 3, it still crosses through 1, but it gets steeper. Base 4 gets steeper than 3, because 3 means tripling, 2 means doubling, 4 means quadrupling. So it gets steeper like this, right? And similarly, if it's getting steeper and closer to the y-axis, then logarithms is the inverse. So instead of getting closer to the y-axis, it should be getting closer to the x-axis. So watch this. When I change the base of n, which is 2, if I change it to now 3, see how it's getting closer to the x-axis? Because it's the inverse. Okay, sorry? Yeah, I could. But then I would have to change the whole slides, yeah. The slides, so if I change the slides to, instead of 10, I can change it to, I think, is that 1,000,000?
Maybe not 1,000,000, maybe it's like 1,000.
1,000, all right, let's do 1,000, okay? And now the scale's to 1,000, I can change this, and you can see how it's getting closer and closer and closer and closer and closer and closer. It's very minuscule changes at this moment, but the shape is still, and don't think that this is actually cut off here. It's not cut off. It's actually really close to the y-axis, but never touches because you have an asymptote. Okay, and it just keeps going and going and going. Okay, but that's what the bases do. So whatever you know for an exponential, it's the same for logarithms. Okay, it's for logarithms, it's just the reverse. That's hopefully giving you a comprehensive understanding of transform. Chapter 7, you're applying it to this, and you can apply that to every functions you're going to learn in methods. Quadratics, cubics, hyperbolas, circles, all of the things I'm teaching you right now is exactly the same for graphs. If you really keep that in mind, you should be able to sketch most graphs instead of see it. Okay? Now, that's 13G, but to add it all together in 13G, I want you to be able to find x-axis intercept, y-axis intercept, which means you have to know the algebra. So let's have a look at a question from 13G. Now, to start off with, I want you can either start off with 1, but it doesn't have translations there. I want you to start off with 4. Okay, so question 4, I'm going to do an example here. And I really want you to take it. I know it's not as hard as the ones I've just shown you in GeoGebra, but I want you to really try to understand the overall concept. So here we go. Let's have a look at this graph here. Let's do this one. Let's do the first one. Simple and easy. Okay, so y, f of x, let's call it y equals to log base 2 x minus 4. Now they've done a pretty easy one. They haven't done a lot of combinations here. There's no vertical translation. There's no reflection. It's a simple to the left or right by 4, right? So let's have a look. We're reading this graph here. What does the x minus 4 do again? What does it tell me?
Translate to the right by 4.
Good. Translates to the right by 4. How do you know? Let it equal to 0. X minus 4, let it equal to 0. X equals 4, so you know it moves to the right 4. So if you were to sketch this graph already, asymptote moves to the right by 4. So here we go, asymptote, label your asymptote, x equals 4, and you know it's a normal log graph, so it looks like this. There's no reflection, there's no dilation, doesn't get thinner or anything. What am I missing right now? X-intercept. So going back to your algebra, how do you find X-intercept again? What do you have to do? How do you find the X-intercept? What do you do? Let y equal to 0. So here we go. This is your y equals log base 2 of x minus 4. You just told me to find out the X-intercept. Let y equal to 0. So here we go. Y equals 0. Log base 2 of x minus 4. Now your goal is to use your algebra from what you've learnt from 13D, 13E to solve this. Your goal is to find x. Your goal is to find this letter here. In order to do that, you have to remove log base 2. Now the question is, what is the inverse or the opposite of log base 2?
Exponential.
Exponential base 2. So when I were to do it, I'm going to do it in green so you can see. I'll be doing, on the left hand side, I do 2 to the power of 0, because it's 0 on the left hand side. And then I'll do the same 2 to the power of log base 2 of x minus 4. See, it looks tricky, but I'm just balancing the equation. You just told me that, what do you do on both sides? You said exponential base 2. So that's what I did. 2 to the power of left, 2 to the power of the right. But then the thing that I know is 2 to the power of log base 2, the inverses, so they cross out. So if this crosses out, what am I left with? Yeah, this now becomes x minus 4, and then 2 to the power 0, which is equal to 1. Now we can solve for x. X has to equal to add 4 on both sides. You see, I'm just balancing the equation. I haven't done anything tricky. I'm just following inverse operations you learned back in year 7. So now I know when y equals 0, x equals 5. So that means this one right here is 5, 0. Label your graph.
That was obvious.
Y equals, yeah, it is 2 of x minus 4. And you're done.
Now we know the
Okay, so you got the shape of the graph, axis intercept,
yeah.
asymptote. I need all 3 to get your 3 marks. Okay, so at the end of the year, when you're doing your exams, that's what I want you to be able to do. I want you to be able to read the transformation, picture what the graph is. There was no need to find the y-intercept, because you know it's not crossing the y-intercept or the y-axis. Find out the x-intercept, label. Okay, but the technique that we only did, that we combined 13E, was right there. This is the only thing I really wanted you to understand from 13E. That log is the inverse of exponential, and exponential is the inverse of log. I'm just balancing the equation right there. Get rid of log base 2, exponential base 2. And that's what it is. Exponential base 2, exponential base 2. I haven't done anything different. Just like you did here, minus 4, add 4, add 4. Same thing. Okay? I want to leave it there. That's 13G. Okay, 13G. Now, depending on where you're sitting at, you're either working on your algebra for logs or you're sketching. But it's one of those two. Same thing with exponentials. You have to have algebra for exponentials, sketching for exponentials. Put them all together, that's applications for the last exercise. Okay, so I've taught you all the basics for chapter 13. It's now on you to work on your algebra or functions. Okay, so next year when you're doing year 12, there are 4 pillars that you have to be able to tick off. One's algebra, one's functions, and the third one, which is calculus, which we'll learn at the end of this year. Okay? You've got 4 pillars for next year, including probability. The 4th one's probability. Stats. You're just gonna learn the whole shebang. But yes, it's very interesting you brought up that question. It's like, why probability? That's why next year's exam, 75% of it is on the 3 pillars. You just need to know all of the bulk learning that you're doing right now in year 11 will give you such an edge for next year. Everything you learn this year is exactly the same for next year. 75% of the course. The only last part, which takes me about 2.5 weeks to teach, is probability. And that's your last pillar. So if you can just nail down algebra, functions, which is what I'm trying to teach you, read the equations, and then you got calculus, which is end of this year. That's it. That's all you got. For 11 and 12, that's all you have to do. And probability, I promise you, you'll pick it up very quickly. Okay, probability is one of those easy ones. It's the first 3 pillars that's hard to get students to work on that. So quadratics, cubics, your square roots and whatnot. Really try to understand what I'm saying. Up, down, left, right, they're all the same. Okay, functions, algebra. Get those for every chapter. Yeah, I don't know. That one, I don't even know where that would fit, actually.